Welcome to the first lecture of the planning stage for our project. Before we explore the technical specifics and development processes, it's crucial to address a few foundational considerations that will guide our decision-making and strategy moving forward. These include choosing between hosting an LLM versus utilizing a model via an API, understanding token usage and its implications, evaluating costs, and comparing different LLMs available in the market. Alright, at the heart of modern AI applications, especially those involving natural language processing, lie LLMs like OpenAI's GPT or Google's BERT and Gemini. As we consider integrating these models into our interview simulator, we face a fundamental choice. Should we opt for self-hosting an LLM or leverage an API provided by platforms like OpenAI, Google Cloud, or Hugging Face? Let's study the first option closely. Hosting an LLM on your own infrastructure means deploying the model on servers or through a managed cloud service. This approach offers maximum control over the model's performance, customization, and data privacy. Self-hosting notably enables model fine-tuning to suit your project needs and keeps all sensitive data in-house. This approach, however, requires substantial computational resources because running and maintaining a model often demands high-performance GPUs and ample storage. Additionally, as the project grows and evolves, the amount of data required to maintain and improve the model's performance also increases, further straining computational resources and increasing costs. So, hosting a model in your environment is more suited to projects where scalability is not a primary concern. This makes it ideal for small-scale applications, such as niche chatbots or specialized tools that operate within controlled environments. Another complication of managing a model in-house is that it requires a deep understanding of AI and machine learning techniques and expertise in server management and network security. For beginners lacking this advanced technical know-how or substantial infrastructure, self-hosting can become a significant challenge. Okay, let's now address the second option: accessing LLMs through APIs offered by third-party providers. This approach can dramatically simplify the integration process. It's user-friendly and requires no specialized hardware or extensive technical background, making it an excellent entry point for new LLM developers. Other advantages of this method include ease of access to LLM technology, scalability to accommodate growing user demands, and flexible pricing models that adapt to your project size and scope. But of course, there are drawbacks. Adding an external service introduces risks related to service availability, security, and potential policy changes that could affect your application. Moreover, the scope for model customization is significantly limited compared to self-hosting and can also be very expensive. Choosing between self-hosting and using an API is a crucial step in the planning process. It's essential to consider your application's specific use case, requirements, and, importantly, the development stage and resources available to your team. For newcomers eager to create LLM applications, starting with an API is the better choice. This option aligns perfectly with our project's goals, so we'll go down the API route. So far, so good, everyone. In the next lesson, we'll discuss another consideration when planning an LLM-powered application: choosing the suitable model. See you shortly. Welcome back. Last time, we discussed the pros and cons of hosting an LLM or accessing it via an API. We opted for the second, more user-friendly option, which doesn't require specialized hardware or advanced technical knowledge. Another critical aspect to consider when working with LLMs is selecting the right model for your project. This strategic choice will significantly influence your application's functionality, user experience, and overall success. One key factor in this decision-making process is whether the LLM is open source or closed source. Open source models are publicly accessible and, depending on their licensing agreements, can often be utilized for commercial purposes. The flexibility of open source models is one of their most significant advantages. Users can fine-tune, fork, or modify these models to better suit their specific needs or integrate seamlessly with their systems. Examples of open source models include BERT, GPT-2, Mistral, Llama 2, BART, and Falcon. When choosing an open source model, consider the number of model parameters. You'll often see this number included in model names. For example, 8B refers to 8 billion parameters. The number of parameters significantly influences a model's capacity to capture complex patterns, but it's not the only factor determining performance. Generally, more parameters can enhance a model's ability to understand intricate relationships in data. But this also means higher computing requirements. For instance, an 8 billion parameter model would need at least 8 gigabytes of GPU memory just for inference if each parameter takes 1 byte. It's important to note that more parameters don't always lead to better performance. Without sufficient high-quality training data and effective training techniques, a larger model may not outperform a smaller one. Therefore, it's crucial to consider not just the number of parameters, but also the size and quality of the training data and the effectiveness of the training process. The number of training tokens a model is exposed to directly affects its ability to perform well across tasks. Models trained on larger, high-quality datasets tend to perform better. Smaller models may be easier to manage and more cost-efficient, but they might lack the robust performance needed for complex applications. And finally, you should consider performance benchmarks and leaderboards. They measure a model's ability to handle a wide range of tasks and rank these models based on their aggregate performance. Hugging Face's Open LLM leaderboard is one of the most popular leaderboards. It provides a comprehensive overview of the top-performing AIs. Closed source refers to models unavailable to the public and can typically be accessed only through an API. These algorithms offer a higher level of convenience and are designed to be scalable and user-friendly. They appeal to a wide range of applications without requiring extensive AI expertise on the user's part. Closed source models, like their open source counterparts, have parameters that you'll have to consider. However, the key difference is that you cannot modify these parameters in closed source models. And while the initial cost for these models via API can be higher due to subscription fees or usage-based pricing, the maintenance is significantly lower. But this convenience comes with a trade-off in terms of customization. Closed source models offer limited flexibility. Users can adjust only certain parameters or choose from predefined options, but not modify the algorithm's core functionality or training data. Some examples of closed source models include GPT-4 and 4o, Gemini, and Claude. Okay, moving forward. When choosing a model, it's essential to carry out in-depth research focusing on multiple important performance indicators. These include fluency, coherence, accuracy, bias, and safety. Fluency and coherence ensure the algorithm's output is clear and logically consistent. Accuracy is vital for the LLM to provide factually correct and relevant responses, especially in applications where misinformation could have significant consequences. Examining bias and safety is crucial to ensure the responses don't perpetuate stereotypes or provide harmful content. Considering these factors in our decision to use APIs, we selected GPT-4o for our project. The GPT models family has become a benchmark for evaluating AI capabilities due to their impressive performance across various applications. While GPT may not necessarily outperform every other LLM in all aspects, its versatility and effectiveness in natural language understanding and generation make it an excellent choice for our needs. Another significant advantage of using OpenAI is its variety of models, allowing us to select the most suitable version for different use cases. Price is, of course, another essential factor in developing any project. Our goal is to create an innovative and accessible product for a broad audience. which means we anticipate substantial traffic and, consequently, higher costs. It's no secret that accessing some of the more advanced GPT models can be costly, which could potentially limit our project's reach. But with careful planning and strategic decision-making, we aim to minimize these costs as much as possible. By carefully choosing the proper GPT model variants to match our specific requirements, we can manage our budget effectively while still harnessing these LLM's powerful capabilities. Alright, that ends our discussion on how to choose the right model. See you in the next one, where we'll examine tokens, an important topic we need to understand in our work with LLMs and, more importantly, when trying to understand their pricing. Alright, everyone. Now that we've established our plan to use OpenAI's GPT models via their API, it's time to explore an essential concept that underpins the functioning of these algorithms: tokens. If you've taken our introductory LLM course with Lauren Newbold, you'll already have a foundational understanding of tokens. However, we'll do a quick revision here to ensure we're all on the same page. Tokens act as the core elements for understanding language in the realm of natural language processing. They serve as the building blocks of LLMs, forming their vocabulary and enabling the models to interpret and generate text effectively. A token can represent a word, a part of a word, or even a single character. For example, the word running might be tokenized into run and ing. The process of breaking down a sentence or a chunk of text into these smaller units is called tokenization. This method allows the model to analyze the text in manageable pieces, making it easier to understand the structure and meaning. Generally, this is how OpenAI recommends counting tokens. Each token is approximately equal to 4 characters in English, or about 3/4 of a word. To clarify, 100 tokens are roughly equivalent to 75 words. For larger text segments, 1 to 2 sentences equal about 30 tokens. A paragraph contains roughly 100 tokens, and 1,500 words equal approximately 2,048 tokens. Each piece of text the model processes, including user prompts and model outputs, contributes to the overall token count. This token count is a vital metric, and it's crucial to be monitored closely in order to effectively manage and optimize the financial side of implementing LLMs in your project. Building on your understanding of tokens and how they're calculated, it's also important to mention the concept of context window and token limit. The context window is essentially the maximum span of text, measured in tokens, that the model can see or consider when processing input and generating output. For example, a model with a context window of 500 tokens can only consider the last 500 tokens of a longer text. If your input is 600 tokens long, the first 100 tokens will be outside the model's view and will not directly affect what the model generates. Token limit, on the other hand, generally refers to a maximum number of tokens that can be included in a single request and response. This limit might be set by the platform or service providing access to the LLM to manage computational load or costs. The token limit might encompass the total number of tokens combined in both the prompt, input text, and the model's response, output text. The distribution of tokens between the prompt and the response can significantly impact the usefulness of the interaction. Let's explore 4 different scenarios to understand the impact of token limits better. Imagine you're working with a limit of 4,000 tokens. In a scenario where the prompt and the response each take up 50% of the token limit, both would be allocated around 2,000 tokens, enough for a detailed prompt and a complete response. That would be your ideal situation. With a short prompt, say around 500 tokens, most of those 4,000 tokens could be used for the model's response. This arrangement suits cases where the question or instructions are straightforward and the desired output is larger. Conversely, a lengthy 3,000 token prompt would allocate just 1/4 of all tokens for generated content. The LLM would squeeze the output into a smaller response, which might not be satisfactory. It will tend to summarize the content, give a brief answer, or sometimes even provide incomplete responses. The least desirable scenario is having overly long prompts approaching the token limit because this can leave insufficient tokens for the model to generate a meaningful response. This constraint often forces the model to summarize content or provide incomplete, sometimes nonsensical, replies. It can even lead to truncated outputs, where the model cuts off mid-sentence or omits critical parts of its response. Navigating these limitations requires a strategic and careful approach to crafting our prompts. Our next lesson tackles another significant factor that directly affects our project's feasibility and scalability: the model's pricing. Welcome back, everyone. Let's jump right into the next topic: pricing. To address the costs of LLMs, it's crucial to grasp the two primary pricing structures: model hosting and pay by token. Let's investigate these strategies, starting with hosting a model. Running a model yourself, whether on your own hardware or using a cloud service like AWS, can be significantly more expensive. For example, an open source model with capabilities approaching those of GPT-4, such as the Falcon 180B, on a cloud platform could cost thousands of dollars per week just in computational and storage expenses. This is why the pay-per-token approach via API access is much more cost-effective and scalable for most applications, especially those just getting started. Let's examine the pricing of the pay-per-token model, which offers a more accessible option because it costs directly aligned with usage. The pricing for different models varies, typically with smaller models being more affordable than their larger counterparts. So, we must balance the cost-performance trade-off. For example, let's consider the GPT-4o model to estimate the cost. We'll use this calculator for the purpose. First, imagine evaluating the expenses for a hypothetical chatbot application serving 1,000 users. Each user posts an average of 7 queries, resulting in approximately 3,000 input tokens, 2,000 generated by the model. This scenario leads to 7,000 executions. Let's write this in the calculator. Next, find the model we're going to use. As you can see, we'll spend around $315. This expense is relatively modest, considering the scale of operations. Of course, there are numerous ways to decrease this cost. The obvious one is switching to GPT 3.5 Turbo. This would cost us 10 times less for the same execution, but would decrease the chatbot's ability. The financial aspect of integrating LLMs into projects cannot be overstated. Whether you host models or employ a pay-per-token service, it's essential to carefully consider the cost implications of your choice. After studying the advantages and disadvantages of different approaches over the last several lectures, we can now consider all the factors and choose the suitable model for our project. We'd first like to access a model without the need for professional equipment or advanced neural network expertise, which naturally leads us to the decision to use an API instead of hosting the model locally. This simplifies the development process and makes it a more financially feasible option for our project. When choosing the most suitable model from the available API accessible options, we must also consider whether to use an open source or closed source model. Given the technical considerations, we've opted for a closed source model, OpenAI's GPT series, because it offers robust support, continuous updates, and reliable performance across various applications. By starting with this approach, we can test our business idea with lower fixed costs and less time investment. If our users respond positively and the project gains traction, we can explore customizing and self-hosting an open source model to optimize performance and reduce costs. This phased strategy allows us to validate our concept quickly while keeping future options open for scaling and improvement. Welcome back. Now that we've established our foundational requirements, it's time to dive into a critical aspect of our technical planning: developing the system prompt. At this stage, you're probably familiar with the different types of messages used in an LLM: system, user, and AI messages. A quick refresher on each will ensure we're all on the same page moving forward. System messages are instructions or commands developers send to the LLM to initiate or control its functions. They may include directives on character impersonation, processing user input, or formatting the AI's responses. So, we'll use the system message to direct the model's actions and methods. These messages define the model's behavior and ensure the interaction follows the intended flow. User messages represent the input from the end users interacting with the LLM, ranging from queries and commands to responses in a conversational exchange. The LLM's ability to accurately understand and process these messages is critical to providing relevant and contextually appropriate outputs. AI messages, in turn, are the responses generated by the LLM based on the system instructions and user input. These messages are the essence of what makes LLMs so revolutionary. Their ability to produce human-like text that is relevant, informative, and engaging. Given this information and the mechanics of our interview tool, you probably know where this is headed. To bring our interview simulator to life, we'll use the system message to instruct the AI on the structure of the interview and the way it should respond. We'll forward the interviewee's responses as user messages, while AI messages will represent the interviewer, guiding the conversation and posing questions. Great! Now, let's focus more intently on system messages, as they're going to be the primary element that shapes this application. The success of our project depends on crafting precise and effective prompts. Let me first insert a couple of important notes here. Firstly, to ensure the integrity and uniqueness of our interview simulator, we've decided to keep the full details of our system prompts confidential, but we'll guide you through the development of the beta version of the prompt created during our initial testing phase, giving you a peek into our process. Secondly, this course focuses on creating a simulation only for the HR part of the data science interview. We've reserved a couple of lectures to discuss the technical questions at the course's end. Alright, let's first examine the interview structure, focusing on the number of questions and its total duration. Real-life data science interviews typically consist of 6 to 8 detailed questions lasting 30 to 40 minutes. We'll implement our interview chatbot to test the interviewee on 6 HR questions. In contrast to real-life interviews where time is tight, our users can take their time and prepare the questions at their own pace. Now, we can brainstorm our prompt. Let's start by recalling the requirements we set in our previous section. As you can see, the second and third steps require the users to select a specific position and company and detail their previous experience and skills. The information they provide should be entered as part of the system message. We can refine the personalization by adding the user's name and position level. With all the essential information now outlined, we're set to craft a prompt template that integrates everything we've gathered. We begin by instructing the AI assistant to act as an HR executive for a specific company, aiming to interview candidates for their desired positions and levels. Next, we provide it with information about the interviewee's experience and skills. We then ask the assistant to include 2 questions from a predefined set of potential questions. Recall that was the last point in our requirements list. Finally, we pass the chat history, which includes previous questions and answers between the AI and the user. This allows the model to understand which questions have already been asked and possibly provide feedback on the responses. Notice the keywords in curly braces? We're using these keywords within curly braces as placeholders to indicate where user-specific data will be incorporated into our prompts. This allows us to mark where personalized information will be included. Currently, we're focusing on crafting the prompts. Details like variable insertion will be addressed in future lectures. With the interview prompt now outlined, our next step is to strategize the implementation of the feedback system. Let's continue with the prompt development by considering what the feedback should include. I like to put myself in the user's shoes and ask questions that I would answer as a user. What insights would be most valuable to me? Ideally,
I'd want an overall score for a quick performance evaluation and a summary highlighting my strengths and areas for improvement. Next, I would wonder, what scoring system would best help me understand my standing and areas for enhancement? A balanced approach would be most beneficial, offering a general performance score for an at-a-glance assessment, along with several detailed metrics that explore specific aspects of my responses. So, let's go back to the drawing board and design a scoring system. Our team settled on a scale from 1 to 10 to provide a nuanced view of the user's performance. This score will be segmented into 4 levels. With the clear evaluation structure now in place, the next step is to determine how the LLM will deliver this feedback. The first method is to extend the prompt template by writing the following text. After 6 questions and answers, evaluate the user's responses. Give an overall score from 1 to 10. Remember that a rating from 1 to 4 renders the candidate unlikely to be considered for the position. A rating from 5 to 6 indicates a slim chance of the interviewee being hired. From 7 to 8, they are considered a promising candidate and a top contender from 9 to 10. Give feedback and write a section on areas of improvement. This approach reduces complexity because only one prompt combines the interview and the feedback process. But the disadvantages include limited flexibility. A single prompt may struggle to handle more complex or diverse tasks that require specialized processing. It may also run into token limits more quickly, restricting the depth of responses. Additionally, overloading the model with too much information at once can lead to off-topic or incorrect outputs due to an incomplete understanding of the information. One concern we've experienced through many trials and errors when we were using the single prompt strategy is that some models might not have a clear understanding of what stage the interview process is at, leading them to prematurely end the interview. We want to maintain control over the process. An alternative strategy involves using a separate LLM specifically for evaluation, which would receive the chat history as context. For the implementation of this second approach, we create the following prompt designed explicitly for the reviewing LLM. You are a helpful tool that evaluates an interviewee's performance based on the given context. Then, we add the evaluation prompt we created earlier. Adopting a separate LLM for evaluating the interview introduces a distinct approach, with its own set of advantages and disadvantages. This method allows for more focused feedback since the evaluation model is dedicated entirely to assessing responses without needing to handle the complexity of conducting the interview. It also prevents the primary interview model from overloading with evaluation tasks and ensures greater control over both the interviews and the feedback. We consider this option when we need a more detailed analysis of the candidate's performance without disrupting the interview flow. And, of course, since we have 2 different models, we can select a cheaper model for conducting the feedback. This way, we can mitigate some financial implications, balancing maintaining high-quality feedback and managing operational costs effectively. This dual LLM approach, however, comes with disadvantages. For starters, it could complicate the system architecture to some extent by requiring additional components to manage communication between the 2 models. It could also increase the overall resource consumption of the application, including processing power and memory usage. This is particularly true when relying on APIs, where increased usage translates to higher expenses, especially when considering scalability. Considering these pros and cons, we've decided that employing 2 separate LLMs and prompts for the interview and evaluation phase might indeed be the more advantageous strategy. Great! With a clear strategy now in place for integrating AI into our project, it's time to turn our attention to the other components of the interview simulator system, the database design and the schema development. See you in the next lesson. Welcome back, everyone. In this lesson, we'll introduce the structure of our database. Understanding the database structure reveals how the system functions behind the scenes, allowing you to design a similar one for your project. So, let's get started. For this discussion, I'll assume you're familiar with the basics of database creation: primary keys, foreign keys, and relationships. But let's have a quick refresher to ensure we're on the same page. A primary key is a unique identifier for each record in a database table. It must contain unique values and cannot contain null values. A foreign key is a column or group of columns in one database table that uniquely identifies a row of another table or the same table. It's essentially a reference to the primary key of another table used to establish a connection between tables. Database relations refer to how tables within a database are connected, often using primary and foreign keys. There are three main types of relationships. One-to-one. Each row in one database is linked to one and only one row in another table. One-to-many. A row in one table can be related to many rows in another table. Many-to-many. Rows in one table can relate to many rows in another and vice versa. This often requires a third table, known as a junction or join table, which holds foreign keys referencing the primary keys in the two other tables. Explore the intricacies of SQL theory with our comprehensive course. Great, now let's look at our table. The positions table, our database's initial table, details 10 positions related to courses on the 365 platform. It features the position name and position ID fields, the latter being the primary key. Following the positions table is the industries table, which lists the most relevant industries in data science. It contains two columns, industry ID as the primary key and industry name for the industry description. The next table is companies, which includes columns for company ID, the primary key, company name, and industry ID. Here, industry ID acts as a foreign key, establishing a link to the industries table. This setup reflects a one-to-many relationship, where each industry may include multiple companies. Lastly, we examine the questions table, which is perhaps the most dynamic of the tables. It features question ID as the primary key. Other fields include question text, position ID, and company ID. The final two serve as foreign keys, linking back to the respective tables. This design allows us to model relationships where one position can be associated with multiple questions, and similarly, one company may have various questions tied to it. Great! Now, we have a solid understanding of the database we'll be using in our application, and a clear picture of how our prompt is structured. See you in the next lesson, where we'll learn about activity diagrams. Alright, we've laid the foundation for our LLM-powered application and introduced its database. Now, it's time to create a clear architectural plan. Just as an architect designs a building blueprint, we must approach our system's architecture precisely. In software development, this refers to the high-level structuring of a system, outlining how components like the LLM, database, and user interface interact to meet technical and business requirements. To visualize this structure and workflow, we use a tool called an activity diagram. Activity diagrams help us map out the flow of processes within our system, showing how different components and decisions interact over time. By using this tool, we can clearly understand how the system operates and make improvements where needed. We'll dedicate this lesson to examining the components of an activity diagram. Let's first introduce the start point, which represents the initiation of the process where the user begins interacting with the system. In our application context, this is when the interview process is triggered and the system starts engaging with the user. Once the process is initiated, we move on to the activities, represented as rounded rectangles. These are the steps performed within the workflow, like answering questions in an interview. As the workflow progresses, it often encounters decision points, depicted as diamond shapes. These decision points introduce branching, directing the flow based on certain conditions. For instance, in an interview, The system could decide which question to ask next based on the candidate's previous answers. After a decision is made, we may need a merge node to connect the alternate paths created by the decision point. A merge node is also represented as a diamond shape, but unlike the decision point, it doesn't introduce new branches. Instead, it consolidates multiple flows back into one, ensuring the process continues along a unified path. As illustrated in the diagram, arrows indicate the flow from one step to the next, showing movement direction and linking each activity and decision point. Sometimes, the workflow needs to split into multiple parallel paths, and this is where a fork comes into play. We represent it by a horizontal or vertical bar with arrows pointing to the simultaneous activities. Eventually, these parallel flows merge back together in what we call a join, again represented by a horizontal or vertical bar. A join brings two or more parallel flows back into a single stream, typically after tasks that began with a fork have been completed. Forks and joins won't appear in the diagram for our interview tool, but I presented them to complete our discussion of activity diagrams. Of course, no diagram would be complete without an endpoint. Just like a journey must have a destination. This symbol marks the conclusion of the process, signaling where everything wraps up. Alright, now that we've covered the basics, our next step is to start creating an activity diagram for our application. See you in the next lesson. Let's bring out the familiar list of requirements which will help in the construction of our activity diagram. It will serve as our checklist, ensuring that every key element is incorporated. And now, let's begin the construction of our diagram with the start point. This is the initiation of the process where the user starts interacting with the system. Note that this doesn't coincide with the start of the interview, an activity that comes later in the diagram. Next, we draw an arrow, indicating that we're moving to the first activity. In the full version of the tool, this activity would correspond to choosing between an HR or technical interview. But as noted earlier, this course will focus only on the HR part of the data science interview. Given that the processes for both types of interviews are fundamentally identical, we can present this more focused and streamlined approach without sacrificing essential skills and knowledge. Now, we need to determine the next step in our diagram. This involves capturing the user's personal information, including name, skills, and experience. So, let's draw a rectangle in the diagram reading Add Personal Information. Next, the user must select the position and level they're applying for. The available ones are junior, mid-level, or senior. Moving on to the next step in our diagram, we need to address the company selection process. Leveraging the database we discussed in previous lessons, users can select a company for which they wish to simulate an interview, with specific questions tailored to that organization's industry and role. To offer greater flexibility, we're also introducing the option for users to create a custom company. This allows them to simulate an interview for a company outside the tool's database, providing a more personalized experience. If users choose this route, they must provide key details about the company, such as the industry, name, description, and required qualifications. This information will then be incorporated into the interview prompt, allowing us to generate questions tailored to the custom company. And finally, for this decision point, users who may not have a specific company in mind or who prefer a more generalized experience will find a third option to start a standard interview. This option allows them to proceed with the interview without specifying a company, using a set of common but relevant questions. With the setup complete, we now move to the core of the process, the interview. This phase is straightforward, concentrating solely on conducting the interview and presenting the user with 6 HR questions. 2 questions will be pulled from a predefined set in our database, while the remaining will be generated based on the user's personal information and conversation flow, creating a customized interview experience. After answering all 6 questions, The interviewee will be redirected to a screen that displays their score and feedback. Now that we've covered all the requirements, let's consider what happens after the user examines their feedback. We'll introduce a decision point to reflect the user's next options. The first option is to retry the interview with the same settings. This allows the user to attempt the interview again using the exact personal information, position, level, and company. The second option is to restart the process entirely. In this case, the user returns to the beginning, setting up the interview anew. These options lead to the endpoint, marking the conclusion of the HR interview process and completing the activity diagram. Great! We now have a clear vision of what we want to build for the final version of the HR interview product. For our prototype, we'll simplify the diagram a bit by focusing only on the core elements. This means we'll remove some of the more complex choices the user can make, creating custom companies or starting standard interviews, keeping only the option to select a company from the tools database, and retrying the interview with the same settings. Our prototype will only allow for restarting the process. We'll concentrate on the essential functionality, ensuring that the core flow of the interview process is intact. The simplified diagram will look like this. As we wrap up this section, remember that the depth and detail you choose to include in your diagrams can vary. Once you start planning and building your own applications, dive as deep as you feel necessary to accurately represent the complexities of your projects. Feel free to try out different layouts, add more decision points, or integrate additional user interactions based on your application.
Alright, everyone! We've made significant progress in this section, transitioning from planning our application's architecture to designing it using activity diagrams. These steps have enabled us to visualize and refine how we'll integrate AI into our application. To summarize, here's how the implementation of the interview tool will unfold. First, we begin with user information collection, where we gather all the necessary details about the user right at the start of the application process. This step is crucial because it sets the foundation for a personalized interview experience. Next, we move on to using predefined questions. We'll pull up 2 questions from our database to craft the interview prompt. This careful selection of questions helps us keep the interview dynamic and realistic, while ensuring a balance between randomness and relevance. Once the prompt is constructed, it's time for the interview execution. Here, we'll employ the GPT-4 model to conduct the interview. The AI will simulate a real-life interview, making the user's experience as authentic and engaging as possible. After the interview wraps up, we enter the final phase, feedback and scoring. We'll capture the entire chat history and use it with another predefined prompt to generate the user's final score. This score reflects their overall performance and offers insights into areas for improvement. Alright, everyone, we're ready to roll up our sleeves and begin coding. In our next section, we'll start building a simplified version of the app, commonly referred to in software development as the prototype. This phase is crucial because it allows us to test our concepts in a real-world scenario and refine our approach based on actual user interactions and feedback. See you there.